let's finish what I'm supposed to tell you. Okay, I cannot complete the entire task. I will adjust this number and tell you up to what you need to know. Okay, now this is very important. It's about hard disk support. This time it's about hard disk support. Previously, I never talk about where you will find the hard disk in the memory architecture. Okay, so actually the memory architecture involve a few members. Why I cannot move? Come on. Okay. So one of the components that is inside the memory architecture, you have register, right, inside the CPU. And I don't know how many of you have read that the data flow diagram before. We call it fetch, decode, and execute. Okay. How many of you don't know about this? Raise your hand. Okay. So I will explain a little bit. So this diagram is like this. When you have a program compiled and it's about to run, you will fetch one instruction from the memory to the CPU. Okay? So that's why we have this diagram. When you need to execute something, you will copy the piece of code into the CPU. And let's say inside the CPU, when it's trying to understand the instruction, let's say this is an instruction, and the instruction is something like this, look like this. I just copy an assembly code like this. And if you know assembly, that means that I want to move a value, that means initialize a register called EAX in the following value. This is wrong. We usually have more symbols to represent a real value, but it's for your eyes only. Okay? So that means that I want to initialize EAX with supposed to be a value, okay? Or maybe it's not a value, it's address, right? It's an address. What is an address? Move the memory value in this address to EAX. Now this is different. You initialize EAX with a constant. That's easy. You're initializing EAX with a memory address will be more complex. Now let's go through the cycle. The cycle first, this instruction go to CPU. The CPU knows that I'm executing. Now this is the function pointer, the real function pointer, which address here. I'm executing this line, so my function pointer is this line. And while I'm executing it, I fetch this address with this result, and notice that the next step is to go to this 0x1234567x. And retrieve its content. Retrieve its content, an integer, maybe this value, and load it into the register. Now this is something that maybe you learn assembly course, maybe you learn microprocessor, maybe you learn computer organization course. We'll all talk about this cycle. I'm here to tell you that this cycle is wrong. Something really, really wrong. What is something wrong about this cycle? It's about this program. This program proves to you that the previous cycle is wrong. What is the proof? Let's run this program first. Okay. So the programs look like this, easy program. I have a PID. Okay, the PID is from the parent process. The parent process called fork create a child process. So you should know that, right? From the first few weeks, you know that the two processes have identical PID variable, but they are separated. They are separated memory. So they can save different values. For the parent, it saves the PID of the child in the PID field. And for the children, for the child process, it will save 0 in PID. So what can you say about this? If I have two separated pieces of memory, it's storing different things. They must be on different memory address. Right? This is as simple as that, based on the previous demonstration of how the CPU works. Okay? Now I will execute this program. Same address. No problem. Run it. So what is this output here? The output is I will print out the PID. Maybe this program is not complete enough. I just print out the PID and the address of the PID. How about I add one more thing? I even add the value saved inside PID. Okay, I'll print address and its value. Okay? Yeah, they're different. Two different processes having two identical variable name, they should be different. But they have the same memory address. Well, with the same memory address, of course they should carry the same value. No. With the same memory address, we have different values. Something wrong, huh? Really in a deep trouble now. It's kind of telling you that all you have learned since the first day you talk about computer, talk about CPU, are wrong. Right? What can you say about this? Okay. Well, this is first time that you try to understand what is going on. Okay. So I think printing out something on from the memory, okay, should be okay, or I cannot get the results. So I think the memory content should be okay. PID should not be anything that being fake, right? Really separated process. The only problem is about the memory address. It seems the memory address is something wrong. I assume these two pieces of memory must be different. Or why can tell me two different values? So they must be different, but we are being cheated. We are being cheated. When we try to print the address, they just give me something the same. Ah, this kind of makes sense, huh? Okay, if you look at it in that way. But in reality, what is really going on is, yeah, for C students will learn this, okay, eventually in the course of 3420. Okay, so MMU design. So what's the MMU? MMU is a hardware. It's already bundled inside every CPU. Okay, since when? Since there's a clear separation. Okay. Arduino, okay, I don't swear exactly. Any MCU, ARM7, okay, they don't have MMU. No MMU for this bunch of CPU. If you are having 3x6, 4x6, Pentium series, they all have MMU. Okay, so 3x6 is already very old. It's approximately 91, 92, something like 91 I'm talking about. Okay, so they all have MMU. This category don't have MMU. What is the MMU? MMU is a piece of hardware, very expensive hardware because it's a cache. Okay, now what is this cache is about? This cache is about translation. So let's take a look at what really happening in the background. The background is doing something like this. Whenever you retrieve an instruction, let's say you want to fetch the instruction pointer or program counter tell me to fetch this memory address. Okay, this is the next instruction. The MMU will stay in the middle and telling you that no. Before you fire this request to, how many of you know there's an architecture called South Bridge, North Bridge architecture? No one knows. Okay, forget about it. I don't want to talk about it. Okay, IOHOP. No one knows. Frontside bus. You don't buy CPU, you guys? Yeah. Okay, forget about this. Okay, this is something that when I buy CPU, I will take a look. Okay, in the very old days. But nowadays you don't need it. Okay. So let's focus back to here. Now, when you want to fetch this instruction, the MMU will say, no, don't follow the instruction. Follow my order. My order is telling me that translate this instruction into another address called AAA00. Okay? And after the translation, it will go to the memory this location, this is supposed to be what we call a physical address. Is 0x8800, okay? Then retrieve the memory, and inside this instruction there is another hard code. The hard code is actually from compiler. The compiler has codes that next step you have to read a piece of memory from 0x12345678 and load it into EAX. Now, how the CPU react to this? The CPU will load this instruction and find that I need an address. Maybe I ask my friend MMU, hey, I want this address. You tell me where exactly it is. And it's telling me that actually it's not 12345678. Okay, in the hardware we know that it is in another address. So you go to another address. So when you pair it up, the pair up is kind of faster. The pair up is there is a range of address, we call it physical address, which is really in the memory. And what are this address? We call this address virtual memory. Something virtual, which is not true. Okay? So why we have the virtual address and the physical address? Okay? Because we want to implement something fancy. What are the fancy things? The virtual address of process X. Let's say the previous demonstration, we have a fork call over the same program. Okay? And the fork call after this tell me that two PID give me the same address. Now we'll have to go back a bit. The two process is actually printing their virtual address. Okay? Let's say in this example, process X, process Y has the same set of virtual address. This guy, and this guy, this guy. They are the same pair. Actually, they will map into different physical address inside the hardware. So it is for the compiler to easily generate any hard coding address. The compiler hard code some address, no problem. In the underlying area inside the memory, it's actually going into two different addresses. For process X, go to here. Process Y, go to here. So this is not something fancy, it's something required, right? You have two processes, you go to two different memory locations, but using the same virtual address. Now, how about another fancy implementation that is really fancy? It's about something like this. What is that? Here's a code. Okay, there is a feature called memory sharing. Okay, we can allow a process to have two virtual address mapped to the same physical address, and to facilitate memory sharing. And this is how share memory. The thread shares the memory, right? I said process can even share memory. This is the true implementation. Yeah, they just map to the same physical address. Okay, so this is the beginning only. Okay, the beginning only. We know that there are two ways to implement this mapping. One, for every virtual address, I map to a new physical address. Okay, or when I want to share some memory, why I can share this memory to two different processes? Because this program won't change. Read only, something read only, then I can share to other people. So this is something which is worth implementing. It's called memory sharing technique. Okay, and the memory sharing is done by we map the virtual address of two different processes, the same virtual address, to the same physical address. Any question you want to ask in this up to this point? Now, up to this point is I didn't tell you how to do the mapping, right? I just tell you that there exists a mapping, and the mapping is governed by a hardware called MMU, okay, memory management unit inside the CPU. Now the problem is who picked up this mapping? Random, not random, okay? Who make up this mapping is the memory implementation, and the technique of this implementation is called paging. Okay, so if you read some very old books, you will find a keyword paging. Okay, but because of the time, I cannot talk about everything about paging. I can only tell you that MMU itself is just a lookup table. Lookup table. So what's the lookup table? Let's imagine that it's an array. Okay, array of virtual address mapped to physical address. Because this is an array, because it's an array, you don't have to implement this column. Well, just that is an array, right? This array address 0, address 1, 2, 3, 4, okay? So as if you have a 2 to the power 32 slot of address. And every address you can map to a physical address and fill every entries and load it into the CPU, right? This is just a simple piece of memory. There's no algorithm, no different implementation, just a very simple piece of memory. Okay, but this is a forbiddable implementation. Forbidding implementation. Why is forbidden? Because of the following calculation. Calculations is telling you that why it's forbidden. Let's imagine that this is a 32-bit CPU. Every 32-bit CPU will remember an address as a 4-byte items. There's 4 bytes, there's 4 bytes, there's 4 bytes. How many entries we have? How many entries? 2 to the power 32 entries. Okay? And every entry is 4 bytes. And together, the CPU needs a memory of 16G. 16G. My computer only have 8G. How did you implement something like this? Okay? So this is not the real implementation. The real implementation, we have 2 layers. What I'm going to tell you is not the real implementation. The real implementation is hidden. From where? I only tell 1 year of OS class about the real implementation. The real implementation is a name called. The name is called TLB. So what's TLB? Translation look aside buffer. TLB. This TLB is not something hard to find. When you look at CPU specification also talk about TLB, okay, which is the real MMU implementation. Let's say Intel Core i7 TLB size. Okay, then you can take a look at Tom's hardware, its own specification inside the Intel. They all talk about the real implementation inside. How big it is, how big is the cache, how big is the look-aside buffer. The look-aside buffer is just another implementation of this stupid thing. Okay, really stupid, 16G, right? So now I will tell you something smart. So what is something smart? Okay, something smart is about, we are not translating the whole 32-bit address. We translate part of it. The significant part, I translate it. The least significant part, I don't translate it. Okay? I just translate 20 bits. Now, if I translate 20 bits, it's easier to implement because it's 32-bit CPU. So every entry is remembered as 4 bytes. You cannot avoid. Okay? So 4 bytes as every entries. But now we only map 20 bits. So the number of items that we have to store will be 2 to the power 20 times 4, which is 2 to the power 22. 2 to the power 22. Okay? 2 to the power 22 is 4 megabytes. Much better. Okay? So I think I have to stop here. And if you want to know more, you can read ahead by yourself. And the thing that I asked in the examination, I think I've cut it off. Okay, it's just very short questions. Okay, during the examination, I've cut it out. Okay, if you want to know more about this whole implementation, you can take a look up to this program. Then you can understand more. Okay, so it's up to 20. Now we have to focus a bit back to the examination. We don't have